Good morning, good afternoon, good evening, whatever the case may be. It's George again. Remember, we left off talking about computational strategies for division, and we were particularly looking at partitive division. And in this session, we're going to continue looking at strategies for division, but we're going to turn to what used to be called long division. We're going to call it modified classical division. But before we do that, let me turn you back to what we're talking about. We're talking about the partitive division principle. So I'm going to go through this a little bit of animation and show you once again what we're doing. We're starting with a set of objects, and the goal is to separate those set of objects into a given number of groups. That's why it's called partitive division. So in this little animation, I distribute those possibly one at a time depending on the grade level. Then we distribute them another object. In this case, we're looking at either colored balls or beach balls. And then I distribute one more time. And then the person who perhaps is distributing these balls out of the dividend set realizes, oh, I'm halfway done. Let me go ahead and distribute the rest of them three at a time. And so I've completed my distribution, and I realize that starting with a set of 24 beach balls, I can distribute those into four groups by putting 6 beach balls or 6 colored balls into each of the groups. And of course, the size of the original set is called the dividend. And the number of groups that we start with is called the divisor, in this case 4. And then the number of objects that end up in each group, remember all the groups are supposed to be of equal size, the number of objects that end up in any one of the groups is 6 in this case. So 24 divided by 4 groups, is equal to 6. That is, there's 6 beach balls in each of the 4 groups. And we looked at a number of different computational strategies to get us to the point we're at today. Now, you might ask, George, why are we looking at so many different computational strategies for division, or for that matter, for addition, for multiplication, for subtraction? Remember, your overall game plan as a teacher, as one teacher among those who are teaching from grades kindergarten through 5th grade, you're trying to accomplish 2 things. You help your kids do 2 things over the course of those 6 grades, and that is to help them to learn to either count or measure in increasingly faster, more efficient, or more sophisticated ways. And the reason for that is the numbers begin to grow in size. We start with little numbers when we're teaching the kids the concepts of addition, multiplication, or subtraction, and then in the 2nd grade, division. But the numbers are going to increase in size, so we have to change the strategy. Sequential counting is not a good strategy when the sizes of the sets are 2- and 3-digit numbers. So we have to find different strategies that progressively get faster, more efficient, more sophisticated. But there's another reason. Another reason, I believe that the more we are able to show our students different perspectives or different ways to look at any one of the arithmetic principles, in this case division, which might include more strategies, I think the better they understand that principle, in this case the principle of division. So there are a couple of ways we're looking at these different computational strategies. The numbers are getting bigger, and we want our kids to have a deeper conceptual understanding of the arithmetic principle that we're looking at. Now we're going to go and turn back to computational strategy. I remind you once again, as I've indicated here on the PowerPoint slide, that the types of objects in the dividend set affect how we interpret the answer, or affect how the quotient is determined. In this case, the objects in the dividend set could either be discrete or continuous. Remember, discrete means they can't continuously be subdivided into smaller and smaller amounts so that it makes sense. You know, breaking up a toy car, breaking up a teddy bear, breaking up a basketball, breaking up a baseball, breaking up a Pokemon card, splitting those into smaller parts doesn't make any sense, okay? Because when you do that, the object you have remaining is no longer one of those objects. It's just a piece of an object. But then there are objects in the dividend set that could be classified as continuous, and those are objects that can be continuously divided into smaller and smaller parts infinitely many times so that each of the smaller parts makes sense. Now, money you might think of as being continuous, but it's not. Once we get down to the penny, we can't break it up into smaller amounts. So money represents a discrete object or discrete unit of measure. But paper, liquids like milk or juice, sand, or things like that, where you can break them up into smaller and smaller parts, that represents continuous objects. So we've already talked about a number of computational strategies for division, and we want to turn to that last computational strategy called, or I call it, modified classical division, because we modify what we used to do as far as division. But I'm going to present a strategy to you in this session so that I think it makes more sense than the old strategy that I learned back under my 3rd and 4th grade teacher. And again, I call it modified classical strategy or modified classical division. Before I do that, however, that strategy requires us to be able to estimate or to figure out sizes. Even when we can't get the exact amount, we want to be able to do something that leads us to approximations. So again, we've been down through this list of computational strategies for division. Again, we're looking at partitive division as we continue from the session we had before, but we're looking at partitive division, and we've gone through all these on the list down through block or group division. And the next thing we want to turn to is estimation with multiplication, and what I mean by that is estimation with division. So let me get into our first item of business, and we're going to talk about estimation. First of all, there are a couple of different ways to estimate or to round. One's called directional rounding, and in directional rounding, we round according to a rule. It's a well-known rule specified many years ago by scientists who wanted to make sure everybody was on the same page. If everyone was approximating the same number, everybody got the same answer, and so they used a rule to do that. And we'll talk about that, and then we're going to go to the topic of undirectional rounding. That's rounding for convenience. So let's go back and review something that you picked up in either middle school or high school when you were in there. It's called directional rounding. And so let's look at a couple of problems. First one we're going to turn to is this number 57,453. So let me get a whiteboard available for us. So let's take the number, I believe it's 57,453. And depending on the circumstances or depending on the problem, we might want to take this number, instead of using the exact number 57,453, we may want to round it to a specified degree of accuracy or a level of accuracy depending on place value. For example, let's suppose that we wanted to look at the digit 5, which is in the tens column. And let's suppose we wanted to take this number and round it to that place value, round it to tens. Well, recall from the public schools that what you did was look immediately to the right of that digit 5, and in this case it's a 3, and we decided that if it's 5 or more, meaning that digit immediately to the 5, which in this case is a 3, if it's a 5 or more, we round up, and we round up by changing the 3 to a 0 and increasing the 5 to a 6. So if we were approximating or rounding to the tens place, it would be 57,400. Now, since it's a 3 and not a 5, what we do if it's 4 or less, we simply keep the digit and truncate. That just means replace the remaining digits by 0. So in this case, if I'm rounding to 5 or the tens place, I look to the right, it's a 3. That's 4 or less. So I replace the 3 by 0 and keep the 5. So I have rounded to the tens place. So this is a rounded number to tens place. Now let's move to the hundreds place, which is a 4. I look to the 4 and I look immediately to the digit to the right. 5. I don't look at the 3. I look only at the digit immediately to the right of the 4, which is in the hundreds place. As I've noted on the screen, if it's 5 or more, I round up. Again, what does that mean? I take the digit 5, increase it to a 6. I'm sorry. Let me back up. I'm rounding to the hundreds place. Let me go back and get my eraser. This is probably from taking a 1,600-mile trip in the last 4 days, so my mind's not quite as clear as it should be. So let me get to the eraser. Go back and let me start back over and remind myself that I'm rounding to the hundreds place. So I'm rounding to the hundreds place. So I'm looking at the 4, which is in the hundreds place. I look at the digit immediately to the right of it. It's a 5. It's 5 or greater. So I take the 4 and I round up. In other words, I increase it by 1 and make the remaining digits 0. That's the meaning of truncate. So if I round to the hundreds place, and instead of using the literal representation, I'm going to use the numerical representation, hundreds place. If I round to the hundreds place, the number 57,453 becomes the number 57,500. Now, if I round to the thousands place, I look at the digit in the thousands place, which is a 7. I look immediately to the right of the 7. It's a 4. And because it's 4 or less, I keep the 7 and change the others to 0. So in rounding this number 57,453 to the thousands place, the rounded number becomes 57,000 exactly. And then if I round to the 10,000s place, around the 10,000s place, again I look at the 5, which is in the 10,000s place. I look at the digit immediately to its right. Immediately to its right, the remaining digits 4, 5, 3 have nothing to do with the rounding process. But I look at 5, I look at the digit to the right. It's 7, which is 5 or more, so I'm going to round up. So the 5 becomes 6, and the rest of the digits become 0. So here's what we have. If we take the number 57,453, if we round to the tens place, which is where the first 5 is to the right, and I look at the digit immediately to its right, it's a 3. Since it's 4 or more, I keep that digit, change the 3 to a 0, and it becomes 57,450. If I round to the hundreds place, I go to the 4. I look at the digit immediately to its right, which is a 5, so I'm going to round up in this case. So the 4 becomes a 5, and the other digits become 0, so it becomes 57,500. In the thousands place, it's a 7. I look to the digit to the right. It's 4 or less, so I keep the 7, make the other 0. And finally, if I look at the 10,000s place digit, which is a 5, look at the digit immediately to the right. It's a 7. It's 5 or bigger, so I increase the 5 to a 6 and make the other 0. Let's look at one more example quickly. And we'll take the number 94,638. And I'll let you help me with this, and you can pause along the way and see it. Let's suppose I have the number 94,638. If I'm going to round to the tens place, and then the hundreds place, then the thousands place, and then finally the 10,000s place, what does the 94,638 get changed to? Let's do the first one together. In the tens place, it's a 3. I look at the digit immediately to its right. It's an 8. That's 5 or bigger. So in this case, this number is going to get changed to 94,600, and because the 8's 5 or bigger, the 3 becomes a 4, and the 1's place becomes 0. Now, what about the hundreds place? Take a moment and do it yourself. What does 94,638 become? Well, it's the hundreds place, so we're focusing on the digit 6. We look only at the digit immediately to its right, 3, not the 8, but just the 3. And because the 3 is 4 or less, this becomes 94,600. We keep the digit 6, make the rest of the digits 0. And then in the thousands place, which is a 4, we'll look immediately to its right, or look at the digit immediately to its right. It's a 6, it's 5 or more. So the 4 gets increased to a 5, so it becomes 95,000. And then if we look at the 10,000s place digit, it's a 9. We look at the digit immediately to its right, it's a 4. It's 4 or less, so it just stays 90,000. And there we have it rounded to the 10,000s place. And again, this is rounding according to a rule. What rule? It's a rule that scientists have come up with so that when everyone is rounding a particular number to a certain place, everybody gets the same answer because they agree to this rounding rule. Now we want to turn back to what's called undirectional rounding. So in our list, we've looked at directional rounding, which is rounding by rule. And now we're going to look at undirectional rounding, which is rounding just for convenience. For example, when we go into a retail store, which might be a clothing store or a grocery store, let's suppose we don't have plastic with us. And so we have a limited amount of resources, but even with plastic, I know there's a limited amount of resources, but you don't always think about it. But let's suppose you have a $20 bill in your pocket and you're going to buy some groceries. You want to make sure when you're going down the aisles and you're putting things in your basket that you're overestimating along the way, because you want to make sure that your grocery list doesn't go over the $20 bill that you have. Let's take a look at an example. So let me go back to full screen view and get me a new page. So you're starting out with let's say a $20 bill, and you start going through and you start picking up items. In fact, you might pick up a loaf of bread, and you notice it's $2.79. Now, you want to make sure you have enough money to pay for the bread, $2.79. Well, if that was the only thing you were getting, the $20 is going to cover it. But let's suppose as you're going along, you sort of mentally say that's $3, okay? And then you go and you get some milk. And let's say you buy milk, and let's suppose it's $3.89. Of course, if you get the high dollar stuff, it's closer to $5, but you can buy milk for $3.89. And here what you might do is round that up to $4. And what you're doing is making sure, well, if I've got $7, I can handle these as long as the taxes doesn't take me over the $7. We'll talk about taxes in just a moment. And then you continue on in your list, and you might go through and you might buy a sugar, 5-pound bag of sugar, and let's suppose that it's $5.38. And again, we could round up, and you might round it up to $5.50 if you can keep track of these things in your head, but I'm just going to round it up to $6. And then I'll continue on. In addition to sugar, you might buy some fruit, and you might buy several kinds of fruit. And let's suppose whatever it is, you know that when you put it all together, it may round up to, let's say, $5. And then you pause and you say, well, let's see, how much money have I spent so far? How much food have I put in my basket? Well, it looks like 3 and 4 is 7, and 6 is 13, and 5 is 18. So far, I've spent no more than $18, because remember, I'm rounding up along the way. And then I have to figure out that I've got tax on this, and in some states, it's taxes on food as low as 5%. In Tennessee, it's about 7%, although taxes in Tennessee are about 9.5%. But you might just say, well, let's sort of guess that on the high end, it's certainly less than 10%. And 10% of $18 is $1.80. And so what you know is this number is smaller than $20. It's, in this case, $19.80. But it's less, whatever the total is, it's got to be less than $20. And that means you've got enough money in your pocket to pay for that. So here's one example of what we call convenience rounding, where you are just approximating numbers, and you're approximating high because you want to make sure you have enough money. And you've made the decision to overestimate in this case rather than to underestimate. Let's look at another example where it might be a driving distance. And again, the setting will help you determine, do I want to overestimate in this case, or do I want to underestimate in this case? And usually the circumstances will give you enough information you can make a wise decision as to what you want to do. Let's suppose you have a car. You're driving along, you have a car, and let's suppose it has a tank. You filled up the gas tank, and suppose the tank holds, let's say 18 gallons. And let's suppose that your car, gets, let's suppose it gets, you think it gets 22 miles per gallon. And you want to make sure that you're getting ready to take a trip. You don't have a lot of money. And I understand I'm making up an example. The circumstances will pretty much tell you what you're going to do. But in this setting, let's suppose that you have to travel 350 miles. And you want to make sure that with a full tank of gas, you can get there without putting any gas in the gas tank. So in this particular setting, what you might decide to do is you can either think of yourself as only having 20 miles, that your car only gets 20 miles per gallon, because you want to make sure you're going to underestimate rather than overestimate. If you're going to go 350 miles and your numbers that you're using to assess whether or not you have, with a full tank of gas, have enough gas to get to your destination, which is 350 miles away, you don't want to overestimate. You don't want to run out of gas. So here's just a situation where you might underestimate, and you might, instead of using 22 miles per gallon, you might use 20 miles per gallon and multiply that, of course, times the number of gallons that you have. So you're getting 20 miles per gallon. If you multiply it times the number of gallons, it will give you an estimate about how far you can travel. And in this case, it turns out with an underestimation using 20, and you're multiplying it times 18, it's really 2 times 18, which is 36, and that on is 360 miles. So you can get 360 miles, and you only have to go 350 miles, and so you're good to go. And instead of underestimating with the miles per gallon, you could have underestimated with the gallons of gas. You could have said, well, let me think that I have only 15 gallons in the gas tank, and I'm going to use that to estimate. So if you had 15 gallons that you were using and you kept the 22, then you could multiply this together. And let's see, 20 times 15, I'm going to do this in my head, kind of a mental math. It's 22 times 15, but 20 times 15 is 300, and then 2 times 15 is 30, so it's 330. And if you use that to estimate, you'll say, well, that might be too coarse an estimate, but at 330, you're going to have to think, do I really have enough gasoline to go all the way? Now you might say, why don't I just go and multiply 18 times 22? Because of your driving speed, you may not get 22 miles per gallon, okay? And you're going to consume the 18 gallons faster than you think you are. So again, what you want to do is estimate, either modifying the 18 gallons or modifying the 22 miles per gallon to make sure you have a number that's bigger than 300 50 miles so that you're confident that when you get there, take into account your speed and all of that, you have enough gasoline to make the trip. So here's an example where underestimating is a good thing to do, while in the previous example with the grocery store purchases or retail store purchases, and you want to make sure you have enough money, you want to overestimate. So these are examples of what I call convenience rounding. Let me go back and look at our PowerPoint page, estimation with division. What we've looked at so far is rounding numbers, using a rule called directional rounding. Then we looked at something called undirectional rounding, where we round for convenience when to make sure we either have enough money or we have a sufficient amount of resources to do or to get to wherever we're going. So finally, we want to look at approximating quotients just to make sure that we're getting close. We don't care whether it's a little bit too big or a little bit too small. We just want a rough estimate about how much something is going to cost or how much time it's going to take to complete this project or whatever. So we're just looking for a close answer. So we want to approximate using a close answer. So look at we'll look at some examples to illustrate what we're talking about. And let's take, for example, just the simple division problem. 745 divided by 63. So the dividend's 745, the divisor is 63. And even though I'm talking about strategies for partitive division, I'm going to show you in a little while in this video session why I can use the same strategies for quotative division problems. For right now, just think that I have 745 objects and I want to divide them equally into 63 groups. How can I do that? Well, I don't want to get into the details of this division. I'm not looking for something that's exact. We're going to turn to a problem like this when we turn to classified or modified classical division. But for right now, I want to show you how to estimate, because we are going to use estimation in that strategy called modified classical division. And so I want to make sure that you feel comfortable in estimating quotients. So here's 745 divided by 63. This is not a compatible pair. So what I want to do is I want to modify this division problem so it actually becomes a compatible pair. And I want to keep the numbers relatively close. For example, if I were to make this a 60 instead of 63, I want to modify the dividend in such a way that it's easily divisible by 60. And one thing might be, if you remember your division facts, I could make this 720, because I know that 60 goes at 720 because I'm a third grader and I know how many times 6 goes into 72. That's one of my division facts that comes out of the multiplication facts. So we know that this is really, dividing 60 into 720. That is like dividing 6 times 10 into 72 times 10. And then 10 divides into 10 one time. So this answer is really 6 into 72, which we know is 12. Now remember, that's an estimate. That's only an estimate, because the actual dividend is 745 and the actual divisor is 63. But I know that this quotient, 720 divided by 60, is pretty close to the actual quotient. I chose to go in this direction. I might have chosen to change the 63 maybe to a 70. And then, wow, I'm going to choose this to be 700. Because 70 divides into a number very easily that's close to 745, in this case 700. I'm going to divide 7 into 700. Again, I can do like I did before. 10 goes into 10 one times. So this is really 7 into 70, and the quotient is 10. Now again, this is only an estimate. When you say is 12 better than 10, not in terms of magnitude. The actual quotient of that number, 745 divided by 63, is in terms of magnitude going to be fairly close to 10 or 12. It might be 11 point something, it might be 13, it might be 9, but it's pretty close to these two numbers. So again, I modified the division problem so as to take advantage of course, friendly numbers. And the quotient I get is only an estimate. It's only an estimate. Let me look at another example. Let's get a new page. Let's take 2,381. Suppose we're looking at the quotient that we might get when we divide by 85. What is that? Once again, I'm not interested in the exact quotient. I want something that's close to that quotient. And so I'm looking to modify both the dividend and the divisor so that the divisor easily divides into the dividend. One way is to make the 85 an 80. And then look over at the 2,381 and find out, okay, what could I approximate this with, which gives me a number that's easily divisible by 80. Well, I think 2,400 is almost jumping out at us. So 2,400 is close to 2,381, and it's easily divisible by 80. In fact, again, this 10 goes in with this 10, and so I'm actually dividing 8 into 240. And if you're wondering what I'm doing, I'm using one of those previous strategies for division, where I can write the 80, the divisor is 8 times 10. I'm writing the 2,400, I could write it as 24 times 100, or 240 times 10. And I can divide in steps, and so I divided 10 into 10. That gives me 8 divided into 240. And so 8 into 240 is like 8 into 24. I add the 0, so this quotient is 30. So 8 goes under 240 30 times. In fact, you can double check. 8 times 30 is 240. So this is an estimate of the quotient 2,381 divided by 85. Instead of making that at 80, let's suppose I chose to make it a 90. If I make it a 90, I want to pick a number that's close to 2,381 that's divisible by 90. And it could be as little as 1,800 or as big as 2,700. So if I make this 2,700, and again, why did I choose 2,700? Because I know that 27 is easily divisible by 9. So again, 10 goes into 10 one times, and then it's 9 into 270, and so the estimate is 9 into 27, 30, add the 0, is 30. So I get an estimate of 30, which happens to be the same as the previous estimate. So both of these are good approximations to what the original quotient would be, or what the quotient would be if I turn back to the original problem, 2,381 divided by 85. Let's look at one more time where we might be estimating quotients. Let's look at 62,039. Now I'm dividing by, let's see, let me turn back. What did I use on my 62,039? What did I use on my 718? 718. Get back to my full screen view. So I use 718. And I want to find out what the quotient is. Now, a little bit later in this session, we're going to use modified classical division to actually find this quotient, or quotient similar to this problem, where you actually have a 3-digit divisor. But for the time being, all we're looking for is an estimate for the quotient of this problem, 62,039 divided by 718. Now again, what are you good at? You're good at single-digit arithmetic, friendly number arithmetic, power 10 arithmetic. So I'm going to take the 718 and I'm going to think of it as the number 700. Now, why do I like the number 700? Well, it's a friendly number. In fact, it's a very friendly number, and it only has one non-zero digit in it, a 7. So 700 is an approximation to 718, so I'm going to use 700 as a divisor instead of using the 718, again, because it's a 3-digit number with at most one non-zero digit, so it has a single non-zero digit of 7. And then I'm going to pick a number over here in this 62,039 that's close to it, that's easily divisible by 7. Well, again, because you've remembered your division facts, you could use 63,000 because you know that 63 is divisible by 7. You know that from your multiplication facts. You know that 7 times 9 is 63. So you know when you perform this division, you can divide 700 into 63,000 fairly easily. I'm going to divide this 100 into this 100 over here to get rid of that part of it. So now I'm only dividing 7 into 630. And again, 7 goes into 630 10 times whatever 7 goes into 63. So 7 goes into 63 9 times, and so 90 is the estimate to the actual quotient of 62,039 divided by 718. One more, maybe instead of using 700, you choose to use 800. There is no better choice. I mean, you're just wanting to get a rough idea of how big the quotient is or what it looks like. And so I'm just taking 718, and in the first case I'm rounding down to 700, and in the next case I'm rounding up to 800. Now I want to choose a number that's close to 62,039 that's easily divisible by 800. Well, again, 62,039, I could either round down to 56,000, but 64,000 is closer to 62,000. So this particular number that I've chosen is going to be a little bit better approximation. So I've chosen 64,000 and divide it by 800. Again, as before, I would divide this 100 into this 100 over here, and I'm left with dividing 8 into 640. Well, 8 goes into 64 8 times and add the 0, so the quotient is 80. Again, it's not the same as the one above where we got 90, but they're the same magnitude. They're a 2-digit number that's not that far away from the actual quotient you would get if you return to the original problem, 62,039 and divided by 718. So here is a way where we can take division and get some estimates. In some cases, we might be overestimating. In some cases, we might be underestimating. So I'm going to turn my attention just for the moment. How do I get, if I'm trying to get an estimate for the quotient Q, what influences whether my quotient that I get is an overestimate or an underestimate? So returning to the PowerPoint slide so you know where we are, down there at the bottom of that page, it says how quotients are influenced. How are quotients influenced? If I want the quotient, if I want the quotient to be bigger, in other words, if I want to overestimate, if I want the quotient to be bigger, there are things that I could do to the dividend or to the divisor that will give me an overestimate. Then we want to find out, well, what underestimates the value of Q? What makes Q smaller? Well, it turns out making the dividend smaller or the divisor larger is what does it. So let's look at that particular setting. Let's suppose what I'm interested in is a bigger Q. And what I'm doing is overestimating. How do I get a bigger Q? Let's think about it. I have a problem. I've got a dividend. I've got a divisor. And when I divide them, it's going to give me a value Q, quotient. Okay, what can I do to the dividend and what can I do to the divisor that will make sure that if I'm approximating, I've got a bigger Q than I would really have? Well, if you think about it, it makes a little bit sense. Makes some sense that if I make D, if I increase D or decrease the divisor, both of these, either one of these, or both will make the quotient, resulting quotient bigger. Let's take a simple example of, let's say, 36 divided by 6. Now, we know that, third graders know that because they know their multiplication facts, and they know that 6 times 6 is 36. So they know the exact quotient is 6. But let's suppose they want to modify either the dividend or the divisor in such a way as to make the quotient bigger. So we're in the case where we're trying to make the quotient bigger. We're trying to overestimate the size of our quotient. Well, in the first case, if I increase the dividend to, let's say, 42, and divide by 6, and I increased it to 42 because I'm trying to give you an example, but I'm also going to pick a number that's easily divisible by 6. So I increased the size of the dividend to 42, and 42 divided by 6 is 7. So this quotient, 7, is bigger than the exact quotient, 6. Now, instead of increasing the dividend, let's keep the dividend. And this time, instead of increasing the size of the dividend, let's reduce the size of the divisor. So this time, let's keep the dividend. Instead of increasing the size of the dividend, let's reduce the size of the divisor. So instead of making that a 6, keeping the 6, let's pick a smaller divisor, but I'm going to pick one that divides into 36 evenly, so I'm going to pick 4. And 36 divided by 4, because I picked a smaller divisor, then I can put more objects out of the dividend into each of the groups, and that is 9. And so in both cases, where I either raise the size of the dividend or I decreased the size of the divisor, that increased the size of the quotient. So here's a way to make a bigger quotient. Make it a bigger dividend or a smaller divisor. Now, let's look at what happens if I want to make a smaller quotient. So here I want to underestimate the quotient. So how can we make the quotient smaller than it was from the original problem? Well, in this case, if I decrease the dividend, that means there's fewer objects to distribute to the groups. That means the quotient's going to be smaller. Or if I increase the divisor, that means there's more groups to distribute the objects in the dividend, so there's going to be fewer objects end up into each of those groups. So in either case, decreasing the dividend or increasing the divisor, or both, will make the resulting quotient smaller. So let's look at an example. Let's take 35 divided by 7. And we know that 35 divided by 7, third graders know this because they know that 7 times some number is 35, and they know it's 5. Or 7 fits into 35 5 times, or if I have 35 cookies and I'm going to distribute those to 7 kids, each kid's going to get 5 cookies. Now, we're trying to figure out what can I do to this quotient problem or this division problem to get a smaller quotient. I don't want the 5, I want something smaller. Okay, well, we said we could decrease the dividend. So we'd make the fewer objects in the dividend, so I could move that down to 28. And again, why am I picking 28? Because 28 is divisible by 7. And 7 fits into 28 4 times. And so I made the quotient smaller. By doing what? By decreasing the size of the dividend. And if I increase the divisor, meaning I have more groups to distribute the objects to, then I can get fewer. I'm going to be able to get fewer objects into each of the groups. So if I increase the divisor, 7, so if I start out and go 35 and divide it by a bigger number, and I should have chosen a different number than 35, but 35 will work. Probably should have chosen 42, but this is okay. If I choose a bigger, increase the size of the divisor, and if I increase it to, I'm going to pick 10. Okay, so I've increased the size of the divisor. That means when I divide 10 into 35, that I'm going to end up with a quotient that's 3.5, which is smaller than the 5. Let me see if I had chosen not 35, but let's suppose I had chosen 42 divided by 7, which is 6. Then if I increase the, if I decrease the size of the divisor from 42 down to 35 divided by 7, and again I picked the 35 to be smaller than the dividend, but yet easily divisible by 7. And by the way, this strategy that I'm using right now is one of the strategies that we're going to use for the modified classical strategy. So I changed the 42 down to 35, making a smaller dividend. That means there are fewer objects to distribute to each of the 7 groups. Then this new quotient is a 5. So I made the quotient smaller. And instead of the 42, let's suppose I increase the size of the divisor. Ran into the same problem. I could choose 8, 9, 10, 11, 12, 13, 14. I really made it a big divisor. I was just looking for something that easily divided into 42, and 14 divides into 42 3 times. But again, I changed the original quotient to one that's smaller. Now this is exactly the situation I want us to focus on. So focus on this situation, and let me remind you of what that situation is. Focus on this situation. What is that situation? If I have a problem, let's suppose I have 376 divided by 58. I certainly want to find out the exact quotient of what 376 divided by 58 is. But in the steps we're going to be looking at for modified classical division or modified classical long division, the step that we're going to repeat is this one. In looking for or in searching for the actual quotient to this problem, I'm going to sneak up on the quotient, but I don't want to have kids erasing things. I want them to always be sneaking up on the quotient from the underneath side. So I'm always going to be looking at smaller quotients that are smaller than the actual quotient to this problem. Now this one may have a remainder, but I want to sneak up on the quotient from the underneath side, which means I want to be underestimating. And what are the things that make us get a smaller quotient so that I'm underestimating? Well, what I want to do is I want to increase the size of the divisor or decrease the size of the dividend. And it turns out I want to do both because I want to make sure that that's an easy problem when I get finished. You noticed how I struggled on the previous example when I had 42 divided by 7. And this one, I want to increase the size of the divisor. And I want to increase it in such a way so that it only has one non-zero single digit. So I'm going to increase this to a 60. In fact, if that had been 51, I still would have increased it to 60. I'm always going to make the divisor bigger. And I'm going to make the dividend smaller. So I'm going to pick a dividend that's smaller than this one. It looks like 360 will do nicely because 36 is easily divisible by 6. And so I made both the divisor bigger and the dividend smaller, and here's what I'm assured of. When I find this quotient, and this quotient turns out to be 6, when I find this quotient, isn't that right, 6? 6 goes into 36 6 times. When I find this quotient 6, I know that 6 is smaller than Q. I want to always be underestimating the actual value of Q so the kids are not required to use an eraser. And not only that, they're performing problems that they can easily do the calculations for. So again, this is the situation we're interested in. So let's turn to that strategy dealing with larger numbers, where that strategy is called modified classical division. So we're looking at modified classical division. It's the classical division strategy, but I modified it so that you, along with your kids, can see exactly what they're doing, because I think things that stay with anyone, whether it's adults or kids, the things that stick are the things that make sense to them, the things that they understand. So let's start with a simple problem where the divisor is a single-digit divisor. And I want to find out what the quotient is in this case. Now, we've already talked about problems like this where we've divided using group or block division, repeated subtraction. Any of those we've talked about up to this point. But I want to look at a different strategy to find this quotient that is called modified classical division. And it's very much like the group division or block division we looked at in our last video session. So again, I'm going to use the notation that you are very familiar with, where I create this little symbolism here. And I put the dividend under that, 6,936, and I put the divisor out in front. Now, there's no reason for modifying this divisor. It's a single-digit number. I can't ask for a better divisor. Those are the kinds of divisors I like. Those with only one non-zero digit. And of course, there's only one digit here, so it's a non-zero digit. So how do I perform the division? So I'm not going to modify the divisor in this case. I could if I wanted to. I could change the 8 by rounding up. Remember, we're always going to be rounding our divisors up and our dividends down, because that makes quotients smaller. Okay, let's think about that again. If I want to sneak up on the quotient of this problem that we're looking at, if I want to sneak up on the quotient, along the way, I want to always be using larger divisors and smaller dividends, because those intermediate quotients are called partial quotients. They sneak up on the actual quotient from the underneath side, and I don't have to use any erasing to find the actual quotient. So in this particular problem, I'm going to take the dividend 6,936, and I'm going to look for a number that's smaller than 6,936 that I can divide easily by 8. So I want to find a number smaller than 6,936 that's divisible by 8. Well, it looks to me like 6,400 is a very nice number relative to division by 8. So 8 fits into 6,400 800 times, because I could write 64 as 64 times 100. And remember, in one of those earlier strategies, I can divide 8 into 100, or I could divide 8 into 64, and then multiply it by the result. So I'm going to choose to divide 8 into 64, which is 8, and multiply it times 100, which is 800. So this is my first approximate quotient, and where I put that 800 to keep track of really doesn't make any difference. I could leave it there. I don't have to write it down anywhere else. But traditionally or classically, we've always wrote it right up here above this number. And so I've written the 800 there above the 6,936. And I actually matched up the place values, but again, I don't have to do that. So my first approximate quotient is 800. Now, when I multiply the first approximate quotient times the divisor, I want to use the actual divisor. Well, this is the actual divisor. You'll see what I mean when I compare it to a 2-digit divisor. But this is the actual divisor. So I have to multiply 800 times 8, and 8 times 8 is 64. So it's 8 times 100, so it's 6400. And what that means is I've distributed 800 of these 6,936 objects into 8 groups each, and it gets rid of 6,400 of the objects in the dividend set. And I'm left with 536. Now, make sure when you're doing this arithmetic that you're not using the what I call old-timey classical standard algorithms. I want to use the ones where I'm counting. If this is a subtraction problem, I'm either counting up or I'm splitting the dividend or I'm doing something. In this case, I counted up. 6,400 to 6,900 is 536 more is 536. Now I want to divide 8 into 536. In other words, I want to distribute the remaining 536 objects out of the dividend set into 8 groups. Well, again, I'm going to pick a number that's a nice number to divide by 8. And I want to make sure it's smaller than 536 because remember, I want to estimate my quotients small. I want to estimate them low. So I'm sneaking up on the actual quotient with the underneath in the underneath side to avoid erasures. So 438, what about 480? That's a number that's smaller than 536, easily divisible by 8. And of course, 8 divides into 48 6 times, then times 0, so this is 60. So I can get rid of 480 objects into 8 groups by distributing them 60 at a time. So the next partial quotient is 60. I'm going to write it right up here above the 800. And then I want to make sure I remind myself how many objects I got rid of. Well, it's 60 in each group times 8 groups. That was 480. Then I perform the subtraction. 480 up to 500 is 20. And then up to 36 is 36 more, so that's 56. And now, if your kids are in the 3rd grade, they'll say, oh, 8 goes into 56 7 times. So they know that 8 goes into 56 7 times. They don't have to use an approximation over here. Oh, they could. I mean, it is 56 divided by 8. They know that's 7. So here are your 3 partial quotients, 800, 60, and 7. And when they add those together, that gives me the true quotient, 867. So the quotient in this problem is 867. So 8 fits into 6,936 867 times. And we could check. We would have to make sure that the 8 groups times the size, 867, when I perform that multiplication by Piaget's conservation number, we have to get back to the original size of the dividend set, which is 6,936. So you'd have to perform that multiplication to make sure that your answer is correct. Now, let me pause for a moment and say, well, what would happen if that number, 6,936, had been, for example, 6,940 divided by 8. So I'm changing the problem. The way I changed it, I changed the dividend so it had 4 more in it. So all these steps would be repeated, except down to this one. It would be 540. And then I would get down here to having 6 more than this one, which would be 4 more than this one, which would be 60. And so when I performed the subtraction and got 56, I would get 4 more. So here's a situation where I have a remainder, but how you deal with that remainder depends on the type of division problem, whether it's a partitive division problem or a quotative division problem. If it's a partitive division problem and the objects are discrete, you're going to have a remainder of 4. But if it's a partitive division problem and the objects are continuous, it means that I have 4 objects. I've got to distribute those into a group of 8. And so if these are cookies and I want to distribute those into 8 parts, then what I have to do is take those 4 cookies and divide them in half. And so this will be each person would get 4/8 of a cookie. Or each person would get a half a cookie more than the 867 cookies that they're already going to get. So again, depending on whether it's partitive or quotative, depends on how you interpret that answer that you get when you're using modified classical division. We'll say a little bit more about this in a couple more problems that we look at. Let's look at another problem, and this time let's look at one where we have a 2-digit divisor. So we're looking at 22,532, and this time we're going to divide by 43. And I want to know what the quotient is and whether it's exact or not. You know, is there a remainder to this problem? I'm going to go through the steps that I just completed where I had a single-digit divisor, but now I have a 2-digit divisor. So I'm going to set the problem up just as we did earlier. So I'm going to take 43, and I'm dividing it into 22,532. Now again, I want you to look at this, you know, as you have a game, and the game is to figure out, you know, how to separate the 22,532 objects evenly into 43 bins, or among 43 kids, or into 43 boxes, or into 43 bags. Remember, we're still on partitive division. Well, it's not easy to work with 2-digit numbers unless they're things that are in the multiplication tables like 11 and 12. And certainly 43 is not in your table. So performing divisions with 43 is not an easy task. So again, we want to sneak up on the quotient, the true quotient of this problem, Q, by getting smaller and smaller quotients that get closer and closer to Q. So how did we do that? We want to increase the size of the divisor, and we want to decrease the size of the dividend. Let me say it again. You want to increase the size of the divisor. That makes quotient smaller. Or you want to decrease the size of the dividend. That makes quotient smaller. In this case, we want to do both because we want to make the intermediate computations easy. So what's a number that's bigger than 43 that only has one non-zero digit? Now, I didn't say closer to 43. I said bigger than 43. So we're going to pick a number that's bigger than 43 that only has one non-zero digit. Well, the next one up the line is 50. So I'm going to use 50 as my approximate divisor. Why? It's bigger than 43. That makes it so that I'm going to be sneaking up on the true quotient from underneath. And it only has one non-zero digit, which makes it so that I can perform divisions easily. Okay, so we picked a divisor that is bigger than 43, so we can compute smaller quotients, and I'm going to compute smaller dividends so that I get smaller quotients. So now I'm going to come over here, and now I'm going to use my approximate divisor 50 rather than the 43 that I'm uncomfortable with. And now I'm going to pick something smaller than my dividend, 22,532, that's easily divisible by 50. Well, I like 20,000. Now your kids are going to choose different numbers depending on their comfort level or their experience. But they're going to pick a divisor that's bigger than 43, that only has one non-zero digit, and they're going to pick dividends along the way that are smaller than their current dividend, and I'm starting with 22,532, and I'm going to choose 20,000. Why? Because 50 divides into 20,000 easily, nicely, and I'm going to perform the division by dividing the 10 into 1,000, which goes 100 times, and then 5 into 24 times. And so do you see why you're going to get a quotient of 400? That one goes out with that one. That one goes out with that one. 5 into 20 is 4, and that's times 100, so it's 400. So my first partial quotient is 400. Now, 400 is definitely smaller than the actual quotient. Why? Because 400 results from using a smaller divisor, by using a larger divisor than is the true divisor, 43. We used 50, and we used a smaller dividend, 20,000, instead of the original dividend, or the actual dividend of 22,532. So I know for sure 400 is smaller than the actual quotient. So I can distribute 400 objects to 50 groups, and it'll give me a total use of 20,000 of the objects. Now, I want to make sure, and here's a step that kids get tripped up on. I want to now use the actual divisor, the 43. I don't want to use the approximate divisor 50, because I'm now wanting to find the actual quotient. So I'm going to multiply 400 times 43. And so you're going to get 2 zeros here, and then you're going to multiply 4 times 43. And so what is that? 4 times 40 is 160, plus 4 times 3 is 12, so 172. I used a multiplication strategy, that we talked about earlier. So if you want to come over here to the side and multiply 400 times 43 and use table array, you can do that. But I did it in my head using table array and got 17,200. Then I perform the subtraction, and I do it by counting up. And I see when I'm counting up, 17,000 to 22,000 is 5,000. And then 200 up to 532 is 332. So the difference between 22,532 and 17,200 is 5,332. So these are the number of objects that I have left to distribute among the 43 groups. Well, again, I'm uncomfortable with trying to figure out how many times 43 fits into 5,332. So again, I'm going to use my approximate divisor, the 50 instead of the 43, and I'm going to pick a number in here that's smaller than the dividend, 5,332, and I'm going to use 5,000. That's a good one. It's smaller than the dividend, and I know how many times 50 fits into 5,000. It fits in there. How many times? 100 times? 5 times 100 is 500. So we're good. So that's my next partial quotient, 100. And once again, now I want to multiply 100 not times the approximate divisor, but by the actual divisor. So now I'm multiplying 100 times 43, or 43 100 is 4,300. Then I'm going to subtract. It looks like counting up. I'm only having to count up 1,000 up to 32. So now I have 1,032 objects to distribute into 43 bins, or among 43 kids. So once again, I'm going to go back to my approximate divisor, 50. And I'm going to pick a number that's smaller than 1,032 that's easily divisible by 50. I think 1,000 is a good number. And again, how many times does 5 go into 100? I think 20. So I put the 20 up here. And again, remember to multiply the 20, not times 50, the approximate divisor, because we only used the divisor to get approximate quotient. Now I want to find out exactly what's happening when I'm using the actual number in the divisor, which is 43, not 50. So 20 times 43 is 0, 6, 8, so it's 860. And then I count up to see how many I have left here. From 160 up to 1,000 is 140, plus 72 is 172. Again, when you perform the subtraction, you can split the menu in. You can use 9's complement. You could use whatever you want to, but I found the difference by hop, skip, and jump, or counting up, 172. Now at this point, your kids may look at that and say, whoa, 43 goes in there, more than 3, maybe 4. And then in their head, they're going to say 4 times 40 is 160, and 4 times 3 is 12, and that's 172. Bingo, that's it. But some of your kids will want to play it safe and say, okay, I don't know that one. I'm going to divide it by 50. So I'm going to pick a number here that's easily divisible by 50, which is 150. It's smaller than 172. 50 fits into 153 times. Then they'll use 3, and let me make some room for my self up there where that Q is. So I've got 3 from dividing 50 into 150, 3, so I put 3 up here. Then I multiply 3, not times 50 now, but 3 times 43. 3 times 43 is, 3 times 40 is 120, and 3 times 3 is 9, so it's 129. Then I perform the subtraction, and I count up 129, 39, 49, 59, 69, plus 3 is 43. So the difference is 43. And then now the kids say, well, 43 fits into 43 one time. And 1 times 43 is 43. So it'd be 43 minus 43, which is 0. So it goes in there evenly. So when I add up the partial quotients, and there are 5 of them, 400 and 100 is 520, add then 4. So the quotient is exact and actually becomes 524. I can check. Is it true that 43 groups times size 524 actually gives me the original dividend D, which is 22,532? And the answer is yes. Very quick review. We started out with a dividend set of size 22,532. We wanted to divide those objects into 43 groups, so 43 is my divisor. I can't handle these numbers as I see them because none of them are compatible pairs for me. So we want to sneak up on the actual quotient by sneaking up using partial quotients that are always smaller than Q. And how do I accomplish that? I want to do it by increasing the size of the divisor to a nice divisor. And what makes it nice? What makes it nice is only one non-zero digit. So in this case, I changed it to 50. And when I go through the steps, dividing by 50, I always want to choose dividends that are smaller. So 20,000 is smaller than 22,532. 5,000 is smaller than 5,332. 1,000 is smaller than 1,032. So I'm always choosing dividends that are smaller, but I'm very careful about how I choose my dividends. I want to make sure that they're easily divisible by the approximate divisor 50. So let's look at another problem. Now, before I leave this one, if I were to modify this problem and maybe change the 32 to a 40, increase it by size 8. That means when I get finished, I'm going to have a remainder of 8. So if I increase this by 8, I'm going to have a remainder of 8. And depending on whether the objects are discrete or continuous, and whether it's partitive division or quotative division, influences what I'm going to do with that 8 as a remainder. And we'll talk about that a little bit later. Okay, let's look at one more problem. Are you ready for a 3-digit divisor? Let's take 45,497 And let's divide it by 719. Now some of you, if you were asked to do this cold, without thinking about the modified classical long division strategy, might make you very nervous. In fact, you just might be overwhelmed with it. But let's go through the steps very carefully and remind you of the overall strategy as we start through this process. First of all, this particular problem is not a compatible pair for anyone in the audience. Probably it's not a compatible pair for anyone on the face of this earth. Okay, so remember what our techniques for developing computational strategies involve. We want to modify the arithmetic along the way so that it takes advantage of what? Friendly numbers, single-digit arithmetic, and power 10 arithmetic. And so, just as I did in the previous two problems, I'm going to do the same thing here. I'm going to modify, along the way, I'm going to modify the problem in such a way that I'm using divisors and dividends that are friendly numbers, involve power 10 arithmetic, and involve divisions that are part of the multiplication facts. They're the division facts that emerge from the multiplication facts that kids, at least in the state of Tennessee, have to learn by the end of the third grade. So we're taking our algorithm involves using single-digit arithmetic, friendly numbers, power 10 arithmetic. So again, let's start out and see if I can save myself a little bit of room, enough room here. So my divisor is 719, and my dividend is a 5-digit number, 45,497. Just as we did before, we want to sneak up on the actual quotient of this original problem where I have a 5-digit dividend and a 3-digit divisor. I want to sneak up on this problem by using numbers that I'm very comfortable with. So once again, I'm going to start off and I'm going to create for myself a very friendly divisor that I can work with. And I want to make it a bigger divisor because remember, bigger divisors, smaller dividends give us smaller quotients. So I want to sneak up on the main quotient Q here in my arithmetic problem. I want to sneak up on that big Q with smaller quotients. So I'm going to choose a divisor that's bigger than 719. That's a friendly number. Well, 720 is bigger than that. 733 is bigger than that. 786 is bigger than that. 780 is bigger than that. But they all have a couple of non-zero digits. I want to get to a number that's bigger than that one that has only one non-zero digit. And I think 800 is a good candidate. It's bigger than 719, and it only involves one non-zero digit. Why? Because kids are very comfortable, at least by the end of grade 3, of dividing by single-digit numbers, especially if they're part of their multiplication facts. So now I'm going to bring the 800 over here because this is the divisor that I'm going to use to get approximate quotients that lead up to the big quotient Q. Now remember, we increase the divisor and decrease the dividend to make sure our quotients are smaller. So I want to pick a dividend that's smaller than 45,497 that I can divide 8 into. So what number is smaller than 45,497 that you can easily divide 800 into? Well, I'm thinking 40,000 is a good number. Now, why do you think I think 40,000 is a good number? Because I can divide 8 easily into 40. And I can divide 100 easily into 1,000. Remember, I can do that. That's one of the earlier strategies we talked about. So I split my divisor into 8 and 100, and I split my dividend into 40 and 1,000. So I'm going to divide 8 into 40. 8 into 40, that's 5. And then 100 into 1,000, that's 10. So my first approximate quotient is 50. I'm going to put the 50 right here. Now remember, I want to multiply the 50, not times the 800. I know what that product is. That's 40,000. But I'm distributing not into 800 bins, but into the actual number of bins, 719 bins. So I've got to make sure I know how to find the product. 50 times 719. Now, how you perform that arithmetic, I don't care. We have a number. We have a table array. We have lattice algorithm. You could use a place value expanded form. You could use a value expanded form. But I want you to go through that arithmetic and tell me what you get. What is 50 times 719? Well, if you were to use a table, it would be what? You would get no 719s. Now this is 50. Okay, so the first one would be 50 times 9, or 700. I'm going to go over to the left-hand side. So you would get this product, 50 times 700, which is what? 35,000. And then it's 50 times 10, which is 500. And then finally 50 times 9, which is 450. I don't know why I put that line there. Now when I add these together, it looks like 35,950. So it's 35,950. Let me pause for a moment and make sure this arithmetic is correct. I was multiplying 50 times 719, so it's 50 times 700. That's 35,000. Then 50 times 10. That's 500, and then 50 times 9, which is 450. So 35,950. That looks good. And then I'm going to subtract, and you can subtract by either counting up or doing whatever it is. But it looks like counting up, I'm going to get what? 9,000 from 35,000 up to 44,000, 9,000, and I've got to get 950, which is 50 up to 36,000. 36,000, 50 up to that, and then on to this number right here. So it's 9,547. So what I need for you to do is to go through and make sure that that number is correct. 9,547. Okay, and so now I want to figure out how many times 719 fits into 9,547. I'm using 800 as my approximate divisor. So what number is smaller than 9,547 that I can divide 800 into? Well, I'm thinking 8,000 is a good number. It's smaller than 9,547. I divide 800 into that, and that goes 10 times 10. And so 10 is my next partial quotient. And then 10 times 719, of course, is 7,190. Then I subtract by counting up again, and the difference is what? I'll let you do this one. 2,357. Okay, and 2,357. And then once again, I could stop right now and say, oh, some of your kids will say, oh, that goes about 3 times, because 3 times 700 is about 2,100. Okay, then those who are a little more careful might, choose to stay with the estimation by going back to the divisor of 800 and picking a number that's not bigger now. You don't want to write down 2,400. You want to write down a number that's smaller than the dividend, that's easily divisible by 1,800, and 1,600 is a good one. So 800 goes into 1,600 2 times. 2 times 719 is 1,438. Then go through the subtraction process. And so when you go through the subtraction process, what do you find? The difference is 919. think that's correct. You can double check my numbers. But then 719 goes into 919 one time. So I'll sneak a 1 up there above the 2. 1 times 719 is 719. Remainder 100. And I'll let you double check to make sure those last computations are okay. But it goes in there, when I subtract 719 going one time, it leaves me with a remainder of 100. And 100 is smaller than the divisor. So the question is, what do I do with that 100? Let's talk about it for a little bit. Get a new age. So we got a remainder of 100, and our divisor was 719. Now, what are we going to do with that remainder of 100? What are we going to do with any remainder that we might get in any division problem? Well, remember, there are two kinds of division, partitive and quotative. And when we use partitive division, there are discrete objects and there are continuous objects. So in this particular problem, where we had a 5-digit number divided by a 3-digit number, 719, the nature of the objects of the dividend set and the affect how we answer this problem. So if it's discrete, meaning something like toy cars or teddy bears or ping pong balls or basketball balls, if we were taking the dividend, which was, if I go back up, the dividend was 45,497. Did I remember that correctly? Yes, okay. So the divisor was 719, the dividend was 45,497. If these objects were discrete, like toy cars, basketballs, ping pong balls, ball bearings, and we were distributing them into bins or boxes or barrels, and there are 719 of them, we found that when we got finished, we could get, what was our quotient? The quotient was, then I guess I didn't even write it down. The quotient was 50, 60, 63. We found out the quotient was 63, and it was the remainder that was 100. So we could take the 45,497 basketballs and distribute those into 719 barrels or boxes by putting 63 basketballs or 63 whatever into each of those 719 bins. But I've got 100 left over. If they're discrete, there's not much I can do with the 100. If they're toy cars, I can't split them up to get them evenly distributed among the 719 boxes, the 719 barrels. So in the discrete situation, the quotient really is 63, and the remainder really is 100. Now, what happens in a continuous setting? Let's suppose that there are, and we will not have a problem like this one, but I'm making it so that you can identify with it. If I had 45,497 cookies, and I wanted to distribute those evenly among 719 kids at your elementary school, and that's a pretty good size elementary school, but let's suppose there's 719 kids there, and you have a truckload of cookies, 45,497. You know that when you perform that arithmetic we just completed, long division, modified classical long division, that each kid's going to get 63 whole cookies. But what are you going to do with those 100 cookies that are left over? Well, if you take each cookie and distribute it evenly among 719 kids, each kid will get one part of 719 pieces that you cut the cookie up into. but yet you have 100 cookies, so you're going to do that 100 times. So each kid is not only going to get 63 whole cookies, they're going to get 100 parts of a cookie that's been split up into 719 parts. And that's an exact answer. So in a discrete setting for partitive division, you have 63 objects distributed to each of the 719 bins, and you have a remainder of 100 because they're discrete objects. You can't cut them up into smaller sizes that make sense. But if they're continuous, you can take the remaining portion of 100 and cut them into parts and distribute those across the 719 bins so that each of the 719 bins receives 63 and 100 719ths cookies. So each kid, if these were kids at the elementary school, they're going to get 63 cookies, and then they're going to get a cookie that size 100 719ths parts of one whole cookie. So here's a situation where you have a remainder, or the quotient is exact, there is no remainder, and it depends on whether the objects are discrete or continuous. In a quotient setting, you again have discrete objects and you have continuous objects, but these have little influence on the outcome. It's usually just the setting of the problem that will tell you what to do with these two numbers when you get finished. So let me go back to our PowerPoint presentation, look at our slides. So we talked about all of these strategies for partitive division, these computational strategies for partitive division in this list down through modified classical division. And the hope is they were all built around place value with understanding. And we talked about the outcomes depending on whether your objects, your dividend set, are discrete or whether they're continuous. Now I want to turn my attention to quotative division, but the good thing about quotative division is all the strategies that we learn for partitive division are the same for quotative division, and let's see why that's the case. Again, very quickly, just to show you how, here is our quotative division principle. This time we've got a set of objects, and now we choose a size that we're going to create for groups of objects. So in this case, in my picture, I'm going to pull out 4 balls at a time, and I want to know how many groups that I can make that are of size 4 balls. So remember the difference between partitive division and quotative division. In partitive division, what is it that we know? We're given a dividend set, and we are given a set of groups that we want to distribute the objects into. So we will know the number of groups. What we won't know is after we distribute the objects out of the dividend set into each of the groups, we won't know what the size of each group is. So the groups are known, the size of each group is unknown, and that's what we're looking for. That's the quotient. The quotient's the size of each of those groups. In quotative division, this time we know the size, but we don't know how many groups we can create with that given size. So very simply, partitive division, you know the number of groups, not the size. In quotative division, you know the size, but not the number of groups. But because it's a number of groups, the answer for a quotative division problem is always going to be a whole number. Let's see why that's the case. So if I go through this little animation for quotative division, I pull out 4, I pull out 4 more, and then I continue this process until I pulled out all the balls that make up groups of size 4, and there's either none left or there may be a few left from which I cannot create groups of size 4. And of course, in this case, the size of the objects left in the dividend would either have to be none, 1, 2, or 3. If there was a group of 4 balls still left in here, I could pull that out and form another group. So the remainder is going to be smaller than the divisor 4. Remainder is going to be 1, 2, or 3, and that's going to be the case whether it's partitive division or quotative division. Always going to be smaller than the divisor. So once again, the list for of strategies, computational strategies for partitive division is the same as the list for quotative division, or I should say the list of computational strategies for quotative division is exactly the same as those computational strategies for partitive division. And the reason is you have a dividend set, and in partitive division, you know the number of groups. And the quotient you're looking for is the size of each of those groups. While in quotative division, you have a dividend set. And this time when you go in and separate the objects in the dividend set, D, you separate them according to size, and you want to know how many groups of that size can you pull out of that. Now, for both of these to be true, this one means that the number of groups times the size of each group better get you back to the dividend set, while this one says that the number of groups, the thing you found, times the size better get back to the dividend set. And so it's just that the groups and the size of the groups are in different positions for partitive and quotative division problem. But they both lead essentially to the same multiplication problem. Therefore, when you're dividing a dividend by a divisor, and you're trying to separate them into groups of an unknown size, or you have the size, which is sitting here, and you want to find out how many groups it is, this strategy that we use for long division is the same, whether the divisor represents groups or it represents size, because of this multiplication fact, Piaget's conservation number. So this strategy works for either partitive or quotative division. Here's what you have to be careful of. When you get finished, you'll have a quotient. And you'll have a remainder. And the question is what do you do with this remainder, depending on whether it's a partitive division problem or quotative division problem, and how do the objects in the dividend set, being discrete or continuous, affect the answers, the outcomes of either of these two problems. And usually it's just a matter of thinking about it. Let me say one last thing before we leave this subject about quotative division. So in a quotative division problem, let's suppose you have 20 rabbits at a pet store, and let's suppose the store owner wants to make sure that he or she has enough rabbit cages to hold all the rabbits, and let's suppose rabbit cages are purchased so that they come in sizes of what are just three rabbit cages. That means each cage is designed to hold or accommodate at most 3 rabbits. Then how many cages do you need? Well, it is a division problem, and notice it's quotative because you have 20 rabbits, and you're going to group them 3 rabbits at a time, and you want to know how many cages are needed, because each cage, you'll need a cage for each of the 3 groups of rabbits. Well, when you go through and answer this problem using any of the computational strategies that we find, you'll find that the quotient is 6 and that there's a remainder of 2. So it turns out you need 6 cages to house 18 rabbits, but you got 2 rabbits left over. But you can't have them hopping all over the pet store without being caged. So both of these numbers lead you to purchase 7 cages, not 6 cages. You need 7 cages. And then there will be problems where your computations, because of the nature of the problem, will choose you to not go up from 6, but to go down from 6. So you'll have a setting where You might get exactly the same answers or calculations, but this time it will require you to go down to 6 cages or 6 objects. And the content of the problem will tell you whether in a quotative division problem, whether you're going to move up to a larger quotient than you originally got or keep the quotient that you got, and the remainder doesn't answer the question. That's not part of the answer to the question. And we'll look at some of those problems in class. Okay, I think that finishes our computational strategies for division. And I don't think there's anything else I need to discuss except this one thing. When you're performing division, make sure you, first of all, identify it as whether it's a partitive division or quotative division problem. Why? Because it influences the answers that you get. And then when you perform a computational strategy, you can use any of the strategies that I outlined for partitive division for quotative division. Doesn't make any difference. The only thing you have to be careful of is how you interpret the answer. And remember, in a quotative division problem, the answer is always a whole number, because it's asking the question, how many groups? Thanks.